Hey everybody, and welcome for those tuning in. This is going to be the second installment of Geochem Live Reviews. So in this one, sorry again, OChem 2 peeps, but we're going to be rolling again with more OChem 1 content. So this will be a review about stereochemistry, SN2, SN1, E1, E2, being able to identify and work with each of those individual reactions, but also being able to, when given a reaction and no one tells you what it is, using our very smart brains and saying, I know that this is an SN2 reaction, I know this is blah, blah, blah. So that's what we're going to be doing today. Sorry that my voice is a little hoarse. I was doing a little bit of yelling this weekend. It was homecoming weekend, so to all my fellow Panthers out there, happy homecoming. And before we get started, I just wanted to say, I have something written down, but I just want to say thanks for obviously tuning in and letting me help you do something that I like to do, and hopefully helping all of you crush it in the OChem world. But make sure to follow me on Instagram at Geochem_IO. Make sure to find me on YouTube and subscribe to my channel so that you guys can see anytime I upload videos or anything like that, because I'm always revamping my content video-wise and such. Make sure to like me on Facebook, because this is where all of these Facebook Live events keep happening. So then you'll get a notification when I go live, so you don't miss the review session and then be sad afterwards. And obviously, check out the site, geochem.io. Tell your friends, tell anyone you know, taking OChem. Tell people that, aren't taking OChem. But if you're here, I appreciate you. I hope your Sunday is not scary right now. I hope it gets less scary. If it is scary because of OChem, we'll make it a little less scary. We'll have a good time. We're going to do, what I want to do is just go through Stereochem, do some problems, really nail down the terminology there, then go individually through SN2, E2, SN1, E1 in that order. Make sure we're all on the same page. We know exactly what to look out for in each reaction. We understand all of the reactions, individual reactions characteristics. So if someone asks you about them, you know exactly what to say or write on a piece of paper. That will be your test. And then we'll do some problems. And quick shout out to my girl at Pitt, Arena. Thank you for sending me some, things to do. So, after we go through all of the things I mentioned, Arena will do some of the problems that you sent me. Not all of them, just because I have some things I have to do today. Not OChem all day. If I could do OChem all day, that'd be the dream. But we'll do some stuff at the very end. So we'll go through the Stereochem, SN1, SN2, E2, E1. We'll do some of the problems sent in. So also next time, for the third exam live review, make sure to send me problems. Be like Arena. Be a good person. Send me things to do. So that's what we'll do. Sorry, I'm a little all over the place, drinking a lot of coffee today. But we'll get started. We'll dive right into Stereochem. We'll have some fun. Okay, cool. So, right off the bat, let's chat about stereochem. So, in organic chemistry, we have three types of kind of like isomerism, big types of like isomerism. If I were to draw something like N-butane, and then I were to draw something like isobutane, right? Both of these bad boys are both C4H10, right? They are both the identical chemical formula, same in both scenarios. However, they're not the same, right? The actual atom-atom connections here, this is just all in a row, a bunch of carbons and hydrogens, right? But down here, we have different atom-to-atom connections, right? These are called structural isomers. We can also have the case where we'll go stick with 4 carbons again. If I were to draw these two things right here, this is trans, like butene, but it's trans, and this is butene, but it's cis, right? Because of what we know, because we're very smart people, we know with p orbitals like this, they have to be parallel to each other, right? So when we have a double bond like that, there's no free rotation about that carbon-carbon bond. So in space, these are actually locked into place like that. So this is structural isomers. These are geometric isomers. So of course, why did I bring that up? Well, we're going to talk about stereochemistry, and there are the type of isomerism in that world is stereoisomers. So the whole shtick of stereochemistry is if I were to draw something like this, a one carbon structure, something like oops, I did that a little bit backwards. Sorry, I wanted this to be this. Ah, here we go. Okay, cool. So if I do something like this one carbon with a bromine, an iodine, a fluorine, and a hydrogen. So the whole deal with stereochemistry is that, yeah, when we do OChem, we draw things on flat pieces of paper, right? But that's not how the real world exists, right? There's 3 dimensions. There's things, in one plane, like if we were to actually consider just this board, right? But when we draw things on flat paper in OChem, you've worked with the this wedge and this dash. Now the wedge actually means something's coming straight out of this board and coming like live at you right into the camera. The dash is our best way to, draw something that would go actually through this board away from us, right? So that's our best way of doing it on flat paper. So stereochemistry is this idea that the way things are actually positioned around a center, this center right here, it actually matters, and it can actually, change a structure's chemical properties drastically. But and I know this is things you guys already know, but what we can do in stereochemistry, right, is we can assign a configuration to something that is attached to 4 different things, right? And that's what we have going on right here. We do have 4 different things. If this carbon had something like this, then we wouldn't even consider this because we're not attached to 4 unique groups, okay? So whenever you're attached to 4 unique groups right here, this is a chiral center right here. So what we can do is a chiral center can either have an R configuration or an S configuration, right? So the way we can assign R and S configurations, we can assign stereochemistry, is we just look at what's attached to our chiral center and we go by molecular weight. We go by who's packing the most pounds. Here, and obviously you have a periodic table, so no worries, obviously. But here, iodine is our heaviest element, so we'll give that a 1. Bromine second, we'll give that a 2. Fluorine is 3, we'll give that a 3. And then hydrogen is dead last, so we'll go 4 right there. And then here's where you get to bring out your molecular steering wheel, and you either get to go like yeet to the right or like yeet to the left. And the sound effects are 100% necessary, mandatory. So what you can do here is draw your little wheel. When you're making a right turn, so this is an R stereo center right here. The last thing I did forget to mention is that we can go ahead and straight up just assign stereochemistry as long as our lightest group, the lowest priority group, is facing away from us. That is part of the convention. The nice part is it's easy for us to work with. It's always a blessing to see the lowest priority group. It doesn't have to be a hydrogen. It could just be it's the lightest group. When it's facing away from us, no worries. If it's facing at us, we can just assign and then take the opposite. Weirdly, so for example, if I were to switch if I put I'm gonna put this here. Let's just say, for example, I switch this H and the iodine. Then we can just redo this problem real quick. I can do, iodine first, bromine second, fluorine third, hydrogen fourth. So you always go in the direction of the 1, 2, 3, which is going to be this way. So it looks like R, but remember what I just said. The lowest priority group is actually facing at us. That's against our convention. It's just the exact opposite of our convention. So instead of just saying, so we can say it looks like R, but it's actually S because the lowest priority group is facing at us. Last thing I want to do is find, as far as assigning R and S, just to make sure we're all on the same page, is I want to make sure you guys are very comfortable with handling the situation when your lowest priority group is neither facing you or facing away from you. So let me just whip up another quick one. By whip up another one, I mean draw what I have on this page right here. If we had this, for example, and just to be clear, deuterium is just hydrogen with an extra neutron, right? So it shows up a lot in stereochemistry problems because it's an easy way to make sure you have another unique thing. Okay, so here, what we would say is chlorine's the heaviest. We'll get a 1. I'm just gonna actually stop what I'm doing. The first one you would probably say is, damn, this is a bit of a shame. My lowest priority group here is hydrogen, and that's in the plane of my paper or board or whatever you're writing on. that makes things a little bit weird because what you technically need to do is like position yourself to look at this molecule from like this angle and do like some mental gymnastics. Shout out Mr. Long for the coined phrase. Royalties are coming. But yeah, you would need to come from this perspective to make sure you actually are assigning things correctly. Or what you can do is what's called the double switch, which I think is personally, and I'm gonna look at I think is a little bit better in my opinion. So so what you can do is if you switch a group in stereochemistry, it's nice because what that does is it inverts your stereochemistry. You would go from R to S or S to R. So what we can do is just switch twice, just to rearrange everything, and then we keep our original stereochemistry and we don't blow our brains out from trying to like do some mental gymnastics. So what I like to do is I want this to end up here. So let me just swap these groups first. Awesome. So I'm not done because I have the opposite stereochemistry now. That's no bueno. We don't want to stay there. However, we're halfway to where we want to be because this is in the position that is easy for us to assign stereochemistry. So I flipped groups once. I just need to do it one more time to regain my original stereochemistry. So here, I'll say I did this. So you can switch any group. So we can switch these two if we want to. Doesn't matter, as long as you just don't switch the ones you switched first. OH. We got a deuterium down here. And we got a chlorine over here. Okay, so perfect. I just want to make it very clear. These are the same. They have the same stereochemistry. Everything's good. We just did some rearranging. So the double switches keeps your original stereochemistry and it prevents you from going insane with doing mental gymnastics. So now we can actually do our job. We can go 1, 2, and 3 because chlorine's the heaviest, then it's oxygen, then it's deuterium. And we can do this, get our molecular steering wheel. We go to the left, which means in stereochemistry world, we have an S configuration. Okay? So it's a blessing, bless up whenever your lowest priority group is either facing you or facing away from you. But if it's in the plane of the board, I like to fall back on the double switch. But if you like doing the mental gymnastics, more power to you. Okay, just wanted to go there on the stereochem front, so we're all on the same page with assigning R and S. Okay, so what is next? Well, I just want to make sure we understand. So stereoisomers are, actually I'll just draw an example. So there are different types of stereoisomers, and I want to look at those relationships right now and how to identify them and how to work with them if someone asks you for, say, a structure's diastereomer, or a diastereomer of a structure, or a structure's enantiomer. So if we look at this right here, we have 2 stereocenters in this problem. There's one here and there's one here, right? And I haven't drawn these in, but they are here. The reason why we know they're stereocenters is because of this carbon and this carbon, we are attached to 4 different things, right? This carbon has a methyl group. This you just treat this as like one giant piece, one thing, right? So there's methyl group, this thing, an iodine, and a hydrogen. Those are 4 unique things. Great, we have a stereocenter. Same thing here, right? We have a bromine, a hydrogen, this ethyl group, and then whatever you would want to call that. So we have 2 carbons attached to 4 different things. Yeehaw, let's assign some stereochemistry. So at this part, this carbon right here, it's awesome because our lowest priority group is facing away from us. It's that little itty bitty hydrogen. So here I'm going to do a bromine. Then here's how you break ties, right? Because from here to here I have a carbon, and here to here I have a carbon. So let me like draw this carbon down here and this carbon here. And I'm just going to make a little list as to what they're attached to, right? So this carbon's attached to an iodine, a hydrogen, and another carbon. This carbon is attached to a carbon and 2 hydrogens, right? So you go with the winner is whoever kind of has like the biggest group at the first point of difference. So right here, right off the bat, iodine is way heavier than carbon. So this is the second group right here, right? The reason why it's not first, right, is because there's a carbon here first. And right here, bromine definitely beats carbon. And then the ethyl group over here is a 3. So at this stereocenter, since we can just assign straight up because our lowest priority group is facing away from us, we are going this way yeet it to the left, that's S, right? Cool. And now let's go through the same thing for this carbon right here. Iodine is first, then we got this giant chunk over here, right? Because even though we have a tie to carbon, this carbon's attached to a bromine, so 1, 2, and 3. So remember, it looks like S, however, our lowest priority group is facing towards us, so we're gonna be smart and take the opposite, right? So at this point, we have an R. So it looks like S, but it's actually R. Okay, so great, we've assigned stereochemistry. So in the land of stereochemistry, we can have things called enantiomers and distereomers. Super hard word to say, always a linguistic fun time saying it. So enantiomers, an enantiomer is when you have a pair of enantiomers, they're a mirror image of each other, right? Think left and right hand. They look like each other, you can't line them up. So whenever you have an enantiomer, if I wanted to draw the enantiomer of this structure, everything is just opposite, right? So if this is RS, the enantiomer here would be, I would need SR. So what you can do is just flip a group, right? We want the opposite stereochemistry at every position. So what I can do is just make the iodine a wedge, make the hydrogen a dash, and then here I will make the bromine a dash and the hydrogen a wedge. And I know with 100% certainty, this will be S, this will be R. That's the enantiomer. A distereomer is basically just a different flavor of the stereoisomer, right? It's just not the enantiomer, but the stereochemistry is different. So a distereomer here could be like the RR distereomer or the SS distereomer, but not the SR, because that is reserved for the enantiomer. So someone asked you to draw a distereomer or something, just change one stereocenter. I'm just going to change this one. So I will use this right here, and I'll keep the other one original. So this would be SR, and this would be SS. Okay, so enantiomer, exact opposite stereochemistry at every location, and distereomer is just different stereochemistry, but it's not the opposite. Okay, cool. Important words to know. Okay, so what do we got next? All right, so I know we're kind of going through this fast. I just want to make sure we have the bulk of the time to do the SN2, the SN1, the E2, the E1. Okay, so one thing that took me personally like a long time to kind of internalize, right, is this idea of chirality, and I kind of didn't lead off with this explanation, but when you're chiral, you have like handedness, right? So to be chiral, the definition is that if a structure is chiral, it has a mirror image that is non-superimposable of itself. So think your left and right hand, right? So if I wanted to know if this was chiral, or if like my hands were a chiral pair, right? This has a mirror image. It's my left hand, the mirror image of my left hand is my right hand. And if I were to superimpose them, line them up, put one on top of the other, they don't line up, right? They can't, they're unique that way. So, and I'm gonna make a blanket statement here, but for the organic chemistry we do, you need a chiral center in a structure to have chirality. So what that means is a chiral center, stereocenter. So you need somewhere that has S or R, right, configuration to have this handedness, to have this chirality, right? So for example, like that structure I just drew right here, or just I'm gonna whip something up that was similar, right? We saw that this had a mirror image. This is a chiral structure because the mirror image of this, of here, is this. These are enantiomers, right? So they are chiral. However, what I want to kind of bring up is the fact that just because you have just because you have locations that have S or R doesn't guarantee that you're chiral. And I'm going to show you an example. And then toss in some more terminology because we like words. Words are fun. All right, so let's take a look at this. We looked at this cyclohexane with two substituents on it. These two locations are chiral centers, right? Because they are certainly attached to four different things, right? Methyl group here, a hydrogen here, and then this path around the ring is not the same as this path, right? Because it's carbon, second carbon, there's a branch, and then here it's carbon, 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 then a branch, right? So there's 4 carbons, 2 carbons. They both are unique locations attached to 4 different things. So if I wanted to assign stereochemistry here, I would go 1, this branch is the highest priority, right? Because there's a tie here, there's a tie here, there's a tie here, there's a tie here. However, this carbon right here is attached to a carbon and then 2 hydrogens. And this carbon up here is attached to a carbon, and a hydrogen, right? So CCH. So that's why for this stereocenter, this path is the first, this path is the second, then the methyl group is third, and also, hallelujah, the H is our lowest priority group and is facing away from us, so we can just have no headache, just assign stereochemistry, and we would go to the left, that's S here, and then I'm going to do this one a little bit faster to get to the explanation, but this would be 1, 2, 3. This is R, because lowest priority group is facing away from us. So here's the thing, right? You would just assume that the mirror image, the enantiomer of this here cyclohexane would just be this, right? However, here's the problem. In stereochem land, when you have a plane of symmetry, right, you are what is called meso. The moment you have a plane of symmetry, right, you are achiral. Chirality goes out the window. It would kind of be like if my hands were like cartoon hands and I had like, 5 identical fingers, and if I had that same setup on this hand, right, I actually would be able to put them on top of one another, right? And that fails the definition of chirality, right? Because to be chiral, you need a pair of things that are non-superimposable. But if you're symmetrical, the mirror image is going to be the same structure and it will align on top of itself. Because the only difference between these two is the fact that I just need to flip this over like a pancake. Yep. Okay, cool. So I will say this. I feel like this is a good like multiple choice question, a true or false question. It would kind of be phrased like to be chiral or a structure is chiral if it has 1 or more stereocenters. And that would be false because if there's a plane of symmetry, which you don't know given that sentence, right, chirality goes out the window. So just to give you a few more kind of like examples and flavors of what it's like when you have a plane of symmetry, just so you can see it. A few things I feel like I've seen that are very common culprits or something like this, because you have that down the middle. Even something like this, which right here, right, because it's right down the middle. But I also hope, that even in addition to that plane of symmetry, this isn't a stereocenter, right? I just drew a dash. The fact is that even though there is a hydrogen, a chlorine, these groups are the same, right? So this fails for symmetry. This is meso. This fails like this is achiral because of the plane of symmetry. This is achiral because it's not attached to 4 unique things. Okay? All right, so that was a little trip through stereochem. I hope you had a wonderful time. However, we need to keep moving because I want to get to the bulk of what this review is really aimed for, and it's the big 4, right? SN2, E2, SN1, E1. So let's start off with SN2. All right, so SN2 is commonly referred to as backside attack. Right, this is one of the 2 substitution reactions you've ran into in your, I'm sure, recent time in OChem. So, I'm just going to go ahead and, the things we like, I'm going to make a little list up here, the things we like for SN2, right, there are conditions that are optimal for SN2. We need a substrate with low hindrance. Substrate, low hindrance, I'm going to abbreviate. By that, we mean something that's methyl or primary, right? I mean, we can do secondary, but ideally we want something that is super accessible, something that's very easy to get to, right? Substrate being the thing that the carbon we're going to attack. And, brain freeze. To add on top of that, right, tertiary never works with SN2. So tertiary carbons is a no-go. So I'm going to draw that and I'm going to cross it out. Okay, so the next thing, things we like for SN2, we need a good nucleophile. Something that is negatively charged, something that is looking to attack and react with a carbon that has a good leaving group. Okay, good LG. That's all. Always need a good leaving group. And the last thing that we need, and I never really understood how big of a tell this is when you get a reaction that you don't know what the reaction kind of path is you need a polar aprotic solvent. Okay, and I'll get to that. Explain why that's good, like ideal for the conditions as well as the ones that commonly are used. So let's look at something like this. Let's do a bromine, something very simple, and then we'll do a more involved problem. Something like this. So, and I'm gonna write acetone down here. Okay, cool. So in this problem, if we're gonna look at this, I would be basically, I'm just telling you that it's an SN2 reaction. If we're gonna look at our list and kind of line up what's in this scenario, and we'll understand why these conditions are good for SN2. So, over the arrow, the first thing we can kind of see is that our negative thing that's going to, there we go. And sorry, I got a call. And we're very low budget, low tech here at Geochem, so I'm using this as my phone. So we here, right? The lover of positive charge. It's this thing right here. He's gonna find something positive. He wants to attack it. He wants to react with it, right? So then, if we look at our substrate, this is the carbon we're dealing with, right? Because this carbon's bonded to a bromine. This is a polar bond, right? Carbon's partially positive because bromine still has electron density. And the carbon's good for attack because we have a primary situation, right? There's not a lot of steric hindrance. It's going to be easy for this hydroxide to actually get in, start bonding to this thing and getting involved, right? Cool. The good leaving group, right? So you look at the thing that we'd be kicking off, and it's going to be this bromine. The game you have to play is, what does this thing look, after it gets kicked off? It's a Br minus, right? The way we can kind of evaluate if something is a good leaving group, nature doesn't do things that's bad for it. Nature likes stability. So we're only going to kick things off if we know that they're going to be fine on their own, right? So this Br minus, this comes from HBr, right? HBr is like, this is the conjugate acid that Br minus would come from. The way we can kind of evaluate, we can use our acid-base knowledge to say, well, this is a strong as heck acid. So Br minus is super weak, super stable, right? So nature likes that. Nature's comfortable with this reaction going forward and kicking off Br minus and producing that. Cool. So, and the polar aprotic solvent. So I'm sure we've all mixed water and oil together, right? They don't mix. In mixing land, like dissolves like. So if you're working with polar and charged things, you're gonna need something that's gonna support, because in real life, this reaction has to run in solution, right? We're dealing with actual, liquids. So to have everything dissolve in solution, right? Because we have polar things and we have some charged species, we need a solvent that's going to support the fact that these things need to exist together and the layers need to mix. So acetone and polar aprotic solvents in general are great for SN2 because the molecules dissolve and everything. However, we want a solvent that's not gonna, mess around with what these two are gonna try to do. When you have a polar aprotic solvent, it's gonna just let the hydroxide do its thing. And on the flip side of that, if we had a polar protic solvent like water, protic meaning you have something electronegative bonded to hydrogen, you get what's called the caging effect, and this water would like crowd this hydroxide and basically bog it down and prevent it from getting to the nucleophile would be hindered getting to the substrate. So polar aprotic solvent is amazing for the fact that you don't get the caging effect. It just lets everybody go and play and let the reaction go. So this is knowing your that little solvent thing is actually a very important tip. You'll see that when we get to SN1 or E1. So in this reaction, in one step, we have the electrons from hydroxide coming in, attacking the carbon right here. At that point in time, right, if I did nothing, I'd break the octet rule. That's a big no-no, obviously. So what we need to do is something needs to leave. A bond needs to break to support the bond that's about to form. That is obviously our leaving group leaving. So if we were to draw an energy diagram for this, it would look like this. Here, I'll draw time on the bottom, doesn't matter. So it's an exothermic reaction, right? So we're gonna obviously have, we'll see this type of energy. We'll start in one place, we'll end lower, right? We'll give off energy. So it's one step, so you have one transition state, one energy hump, that's right here, okay? So if someone ever asked you to draw the transition state for an SN2 reaction, what you would need to do, I'm gonna go ahead and draw kind of like this carbon right here, down here. So I'm gonna draw this dotted line, that's gonna show bromine leaving. At the same time, there's this other dotted line of hydroxide forming, and I'm just gonna fill in the other things like this, hydrogen, hydrogen, and there's like a CH3 up here. So that would be the transition state. It's very important to know that this is a concerted mechanism, right? Concerted just meaning it happens at one step. This bond forms as that bond breaks, okay? All right, so that is a good bit. Oh, the last thing I forgot to mention is if we wanted to, someone might ever ask you about the rate of this reaction. What's SN2, right? So this means substitution bimolecular. So the rate law is going to be some constant K. We don't care about that. And the rate depends on the concentration of substrate and nucleophile. So the reaction goes faster if you dump more of this in and more of this in. So if someone said, how much faster would the reaction rate go if you quadrupled your nucleophile concentration? Well, the rate goes up by 4. Or if someone is funny and they're like, well, what happens if you triple your nucleophile but then cut your substrate by 1/3? Right, so that would kind of just be like, right, this would be tripling my nucleophile, cutting my substrate like by 1/3. Well, the rate stays the same, right? Because 3 and the 1/3 and the 3 multiply just 1. So just know that depends on both, okay? So the one thing we have not talked about in SN2 thus far is when you do SN2 and you're attacking something that has stereochemistry, you must invert the stereochemistry. So picture like you're walking down the street and you have an umbrella and a big lot of wind comes by and just flips your umbrella inside out. That's kind of what we're thinking when we do SN2 on a chiral center. So let's look at this. Obviously we'll do an example because that's how everything is best seen. So let me just draw this right here. If I had something like this, okay. So if we had this problem, and we know this is SN2, so if we're going to go through our kind of our checklist of why is this a good SN2 reaction, right? We have a polar aprotic solvent. We know that's going to let things dissolve in solution and it's not going to bog down our nucleophile, so that's good. We see our substrate right here is primary, right? Because it's attached to one carbon. Our nucleophile here is this O-methyl right here, this methoxide, and which is good. And we have a good leaving group in Cl, what will be Cl-, right? Which comes from HCl, which is a strong acid. Cl- is a good weak stable base. So 4 checks. Okay, so we know that this is going to happen. The oxygen comes in with the electron pair, attacks the carbon, and the leaving group then leaves. One step, right? Okay, so I can't just slap the O-methyl on there and call it a day. Well, I mean, I can, I'm just not going to get any points for it, right? What needs to happen is I need to, like I said, this is what I will not do. If I did this, yes, I just ceased to be dashed. Yes, I, completed the reaction and my regiochemistry is correct, right? Like atom-atom connections. My stereochemistry is wrong. So the stereochemistry here would be 1, 2, 3. It looks like S, and it is because lowest priority group is facing away from us. So I better get R in my product, right? But right now, I still have the same stereochemistry, right? I still have S. So what I personally like to do, again, to each their own, is it's very easy as long as the group you just replaced in is the same priority, so your priorities don't switch, which is the case, right? Because I just added something that's still first priority. You can just flip a group. So I think it's easiest to just say, I'm just going to do this. Because every time you switch a pair of groups, you get the opposite stereochemistry. So that's what I personally like to do. But just remember this, when you do SN2, of course you have to go through your checklist and make sure that everything's good and dandy. However, just remember, if you're doing if you're attacking something that has stereochemistry, the carbon that you're working with, just make sure you remember to change the stereochemistry and get all your points because you deserve them. Okay, so let's do one more and then we'll move on to E2. Okay, so I'm gonna flip my paper. Oh, yeah, and you know what? This will be a good opportunity to see a couple more polar aprotic solvents. We'll do this. So there's something called DMF. So usually your good polar aprotic solvents are acetone, DMF, and DMSO. I would be familiar with these structures because, like, if it mattered that you needed to kind of draw the structure, because sometimes people ask for that, you know it, and you get points for that. DMF looks like, oh, of course I'm gonna no, I think I got it. Dimethylformamide. Yep, it's that right there. DMSO is this right here. It looks just like acetone, which is kind of nice. It's just like there's a random sulfur in there. So remember the polar aprotic because there's obviously some polar bonds in these structures, but nowhere in these structures, right, do you see something like oxygen bonded directly to hydrogen, or nitrogen bonded directly to hydrogen, or even chlorine bonded directly to hydrogen, right? Because that's what makes something polar aprotic, is when you got a very strong partial positive charge on a hydrogen. Okay? So in this case, we're rocking with DMF. Doesn't make a difference at all. So what's nice here is you can like almost let your hair down. Woof, there's no stereochemistry on this carbon that I'm attacking, which is kind of nice. So you're just here to go make sure your 4 checks are good, and we can actually just do the attack. Our nucleophile here is I-, which is a great nucleophile. It's super negative, right? That's what we love to see for something that we want something negative that wants to seek out something positive. Our leading group here is Br-. We love that too. That's a good, weak, stable base. Primary carbon, we love that. Super accessible. The sterics are not going to cause an issue for the SN2 attack. So in one step, right, we're going to have I- come in, attack that carbon, and while that bond is forming, the CBr bond is breaking. So we don't have to worry about stereochemistry at all. You can just kind of do a very simple replace. Okay? And then, woo, you got it right, super, hands up. Cool. All right, we are now experts in the land of SN2. So let's move on to E2. But I'm also very bad about, like, I have like my computer set up. I don't know if anyone's writing any comments. Let me just check real quick. Doesn't look like that is the case. So we will keep going. E2, right. So again, I'm gonna kind of like reuse this list a little bit, and I'm just gonna replace some things. So it's important to know that E2 and SN2 like are competing reactions, right? Anytime you're doing SN2, there's always like I don't want to say a risk, but like there's always the potential for E2 to occur at the same time, right? They're like 2 sides of a coin, right? So instead of for SN2 we like low sterics. For E2 we want high sterics. And we still want a good leading group, we still want a polar aprotic solvent, but instead of a good nucleophile, we want a good base. Good, strong base. And this was something that was kind of hard for me to kind of mentally grasp, but I think let's explain it really quickly so we're all on the same page. So something like I- is a great nucleophile, right? We know it's a lover of positive charge, but remember we said like something like I- comes from HI, right? Well, this is a very strong acid, which means this is a crappy base, right? It's super weak, super stable. And that's okay, it's just not a good base. However, it's a great nucleophile. Now let's take, for example, something like NH2 minus. So NH3, ammonia, has a pKa of roughly 35. So remember, the lower your pKa is, the better acid you are, right? Well, if you force ammonia with a pKa of 35, if we deprotonated it, if we force it to be an acid, which it's not good at, well, you get NH2 minus, right? So if this is a weak acid, then this puppy is a super spelled fun, super strong base. So it's important to know that yes, bases are negative. Good bases are negative. Nucleophiles are negative, right? That's just part of the job description. But just because you're negative doesn't mean you're good at either thing, or one thing or both. So I minus, something like this, like these are both capable of doing SN2 for sure. But in the land of E2, I minus is not going to help us out. Something like NH2 minus will help us out. So I just wanted to squash that right off the bat. Okay, so for E2, let's look at a sample reaction, and then we'll get a little bit more into the nitty gritty. So if we had something like this, so I hope, so if we look at our list of things we want for E2, it's going to be kind of fun to compare this back to SN2 now that we know, for sure everything about SN2 that we need to know, and say, oh, well, yeah, SN2 is not going to happen here. So right off the bat, we know that we have OH minus, which is an intermediate base. Like, it can definitely do E2, it can definitely do SN2. So let's keep looking at what else we got. We do have a polar aprotic solvent, which is good. That's going to allow us to do our thing, and we're going to have no caging issue. Our substrate is tertiary. So remember, that means no SN2. There's absolutely no possibility of it happening at all. Not even a little. Not even an inkling of a possibility. So, and we have a good leaving group, Br minus, right? So E2, what's it about? What's the mechanism look like? In one step, concerted, just like SN2, you look at a neighbor, you go to the carbon you're working with, you go to that carbon's neighbor. You're saying, okay, I need a proton to work with, and because we're gonna abstract it. So this OH minus will act as a base, and it's gonna grab this hydrogen, this H, this proton. It's going to take none of these electrons with it. These electrons are going to swing up over here and start to form a double bond. At the same time that this bond is forming, this bond's moving, this bond breaks all at once. So then you get something like this. So if you were to draw the transition state, it would kind of look something like this. And it's not going to be pretty, but it'll work. And then something like that. Just basically showing all the dotted lines of where bonds are forming and breaking. Remember, one step. So if someone said, draw the energy diagram, I hope you're saying at your computers, saying, haha, one step, one transition state, one hump, right? We'll draw exothermic diagram profile, and it'll look like that. This transition state appears right up there, okay? Cool. So there's a little bit more that we need to unravel with E2, so let's just keep going. So with E2, we like sterics. That's going to help us get more E2 product, more E2 reaction. The thing is, though, you don't need to have those sterics. Those sterics don't need to necessarily come from your substrate, though. So if we had something like this, you know what, we use something different. We use a tosylate in OTS. Good leaving group. All right. So let's say, for example, sorry, my nose is very itchy. Oh, ooh wee. Oh, okay. So let's say we just had two reactions, kind of right here. So in this scenario, if I used, NaNH2, some DMSO, we don't have like a symmetrical situation going on here, right? Because if I'm going to do E2 here, I could pull off this proton or one of these protons, right? Like, which double bond do I make? So when you have a small base, which is what NH2 minus is, and when I say large base, I mean these are like standard bases that everybody uses. This is potassium tert butoxide, T-butoxide, if you will. This is LDA. So if you have either of these are your big bulky bases. These are your go-tos to do E2. Because the steric hindrance comes from the base you're using, and not, you're not banking on the substrate itself to have a steric situation, So when you have a small base, you go to make the most substituted double bond. And by most substituted double bond, I mean it's the carbons in the double bond are attached to more carbons. So because this would be between a secondary and a tertiary carbon versus a secondary and a primary, with a small base, we're going to make this double bond right here. When you have a more substituted double bond, when the carbons in your double bond are attached to more things, it's a more stable double bond. So energetically ideal. So here we can draw the mechanism. We would abstract the proton here. These electrons swing down, leaving group leaves. We make this structure, and our double bond is, because it's like from there we're bonded to two things, we're bonded to one thing here. This is a tri-substituted double bond. Okay, so, but for example, let's say if I used T-butoxide down here. So in fact, because this thing is so big and bulky, he's going to be a little lazy. Lazy, and he's going to see this situation and go, oh man, really? Do I have to get that hydrogen like a little chunky, carrying the winter weight? Is it just easy for me to grab that hydrogen? And in fact, that's what happens. So when you use a big bulky base, you go for what will be the least substituted double bond, because it's the easiest hydrogen for this base to abstract. So I'm going to go ahead and just draw the product. So up here, it's important to note that in this reaction going this way, this is the major, and you will form a minor product of this, and then down below it's flipped. This is your major with a minor of that, okay? And if you want to put names to these, this is like the Saytzeff product when you use like when you get like the most substituted double bond, but then when you form the least substituted double bond, that's called the Hofmann product. Okay? Cool. And I always spell Hofmann wrong. I never know if it's one F, and Saytzeff spelled a whole different bunch of ways. So if I wrote that and you're like, Joe's whack, like I've seen it spelled like with a Z in the beginning, you're probably right. It has been spelled that way, which is fun. So just know that you don't always just make the Saytzeff product. If you have the big bulky base, remember to go Hofmann. All right, so there's one more little quirk with E2 we need to kind of go over. And it's kind of something that we should have technically been doing from the beginning, but we had to understand E2 first before we can introduce this concept. So, just erase this. So in E2, right, we go from something like this to something like this, right? We actually make a double bond, we make a pi bond, right? So from here to here, we actually have a set of p orbitals that we've created that gets set up to obviously have the double bond. So when you're doing elimination, if you're leaving group, I'm just going to use bromine. I'm just going to draw kind of like a cutout section of like where the hydrogen gets ripped off, the electrons make the double bond, the leaving group leaves. You need to have a type of setup where the hydrogen you're going to eliminate, here I'm going to use hydroxide as a base, it's opposite to the bromine that's getting eliminated. Like you need this type of situation, which also doubles as a great party dance. So you need to have this anti-relationship between them. If that sounds familiar from your time doing Newman projection stuff, then it's the same word. You need to have this up and down relationship because it supports the setup of the p orbitals. This phenomenon is called, like you need the hydrogen you eliminate and the leaving group that leaves, they need to be anti-peri planar to each other. That's the relationship they need to have, anti-peri planar, right? It's a very funky R. Because if you have cis-peri planar, same side, this doesn't fly. It doesn't support the setup of the p orbitals. So in fact, when you do E2 problems, you need to look for, basically you say, this is where I want to do my elimination between these two carbons, and that's where I want the double bond to be set up. You have to check if the anti-peri planar requirement is fulfilled. Otherwise, you just can't do the elimination. So let me show you an example. Okay. Look at something like this. Just drawing in the methyls to make them very obvious that what they are. Okay, so let's say we did something like this, and I'm going to go ahead and use, we'll use NH2 minus one more time, why not? And we'll use DMF. So if we go through our checklist, we got a polar product solvent, that's good, that's a check. NH2 minus, strong base, that's a check. Here, right, our substrate is tertiary, so zero potential for SN2, and we have a chlorine, good leaving group, so check, check. Okay, so I have a small base. I want to make the Saytzeff product, the most substituted double bond, right? That's the best outcome given the fact that my base can actually get in there because it's tiny. So I see this tertiary carbon, obviously I have to work with him, but the neighbor, I can either work with a secondary neighbor or a tertiary neighbor. So this is ideally what I want to do. However, I'm smart and I know I need to check for the anti-peri planar requirement. So because the chlorine, my leaving group, is a dash, the hydrogen I'm going to eliminate has to be a wedge, right? Because that's dashes down, wedges up. This would be anti, right? Unfortunately, the hydrogen I want to eliminate here, it's a dash. So it's at this point that you say, haha, I found the trick. I can't do the elimination this way. I have to do it the other way. So at this point, it's not the elimination we wanted to do, but it's the elimination that it's the only one we can do. So we'll draw the mechanism. I'm going to do this. Didn't touch this up here at all, right? Because we couldn't work with it. Double bond here, and remember, anytime you have an sp2 carbon, right, like that, our geometry is planar, flat. There's no wedges and dashes. So the thing that unfortunately kids lose points on is when you draw, like when you have this type of situation going and you have something that was a wedge or a dash, just make sure, sorry about that, just make sure that this flips to a straight line. Okay? So that's always a guide. So if you did this, it would be unfortunately not right. You might just get dinged a couple points. Make sure whenever you have an sp2 any sp2 carbon, anything branched off of it is a straight line. Okay? Cool. That's E2 in all of its glory, all of its little quirks and tricks. So let's move on. We'll plunge into polar product land and get nice and cozy with SN1 and E1. Then we'll do some problems. Then Arena, we'll do some of your stuff, and then we'll call it a day. So SN1, cool. All right, so I'm going to revise our list up again here. So even though it's the same thing, high sterics, I just want to say like we need like the substrate we want to work with, like we need like highly substituted, which just means highly substituted means like secondary, tertiary. That's what we want to work with, the carbons in SN1. Not a good base. We still need a good leaving group, but here we kind of need like we need like a weak nucleophile. I'll explain why in a sec. And instead of polar product, that's right, ladies and germs, polar product. That's what we're dealing with. That's why knowing your solvents is such a big win, because if it's polar aprotic, you know it's SN2E2, but if it's polar protic, you know it's going to be SN1E1. So literally, knowing your solvents cuts the decisions you have to make kind of in half. Okay, so SN1. So one thing I will say is that it's the rate law. I forgot to say it for E2, but it's E2. Just like SN2, the rate law depends on both concentrations of stuff. For SN1, we only have to, the rate is only determined by the concentration of substrate, and I'll explain this in just a second. So let's do an example reaction. So if we had something like this, little isopropyl bromide, and I threw in some water like this, we end up getting this. So in this SN1 reaction, the very first thing that's going to happen is this leaving group is going to get surrounded by the solvent. And you don't ever have to draw this. I'm just doing this for the sake of the explanation. The solvent's going to get all cozy with the leaving group. All of these hydrogens have a big fat delta plus on them from their polar bond with oxygen. Eventually, they're just going to kind of be whispering in bromine's ear like, hey, you want to get out of here? Bromine says, yeah, sure, why not? So bromine leaves all by itself. And in this step, this is a step called solvolysis because the solvent is breaking a bond, solve, lysis, yeah? At that point, this carbon loses a bond, it's positively charged, it's a carbocation. Very reactive, right? Like carbon does not have a full octet anymore, so this thing is ready to roll. It's looking to react with somebody. That's why it's good in that's why in SN1 we need something that's a weak nucleophile because we don't want it to react right away. We want it to sit back, let solvolysis happen, and then this thing that's not great at reacting, it's not very good nucleophile, it has an electrophile that's really reactive, so it can do its job now. So water floats on in at this point in time and actually does the attack because this carbon's begging for some electrons, begging someone to fill the octet. Okay, oxygen now has a positive charge right there. Everyone has a full octet, right? But oxygen's not happy with that positive charge. We know he's an electronegative type of guy. He does not enjoy having that positive formal charge. So another water or even the leaving group you kicked off in the beginning, we'll just mosey back on along and just do a cleanup step like this. And that's how you get your final product. Okay? So a few things I want to pick apart here. So the rate law. The rate law is obvious now, or it's easy to explain because the reaction, the SN1 reaction, it does not matter how much damn water we would dump into this hypothetical reaction mixture. The reaction goes as fast as this step goes, right? This is the rate determining step. Nothing else happens. The water is not even involved until the carbocation is formed. So the more carbocation you have, the more SN1 you can do, the faster it can go. So that's why the rate law is determined by just the concentration of the substrate, not your nucleophile. That's a pretty popular question to ask on tests. And then the other thing I wanted to do is let's draw an energy diagram because they're super fun. Why not? So this is weird because in SN2 and E2, life was breezy. It was one step, man. No big deal. It's a little bit more involved here, right? So what I like to do is I like to look at each step and then draw a little like tick on my energy diagram to say, okay, here's where I started, here's where I went, because I either went up in energy or lower in energy, right? So first, from here to here, it's solvolysis. I hope you're thinking to yourselves, well, I went from something to something more unstable, right? So pick your starting place, but I hope you are thinking in the solvolysis step is endothermic, right? We go from something here, and we actually go up in energy, right? It's very common to forget that you just have to think about kind of energy diagrams. Up is like you're getting more unstable. So and here, from here to here, that's we went up in energy, right? And that's this intermediate right here. So then from here to here, right, we have a big step happen. We have an attack, and then everyone's octet is full. So we're definitely getting more stable here. So from here to like here, why not? But we're not completely done, right? We have the little acid base step right here where we get the full like product, and they're close in energy, right? Like obviously this is a little higher in energy because the oxygen's not super pumped about that positive charge. So I think this is kind of what the skeleton would look like, and then now you get to play like Roller Coaster Tycoon or Ochem Edition, and just go like woo, woo, like that. Sound effects, again, necessary. So, and I love how I didn't really do like a, should have There we go. Something like that. Something that looks a little bit nicer than that. But it's important to just be like, I have this many kind of states. I need to do like a little transition state for each of my little humps that I need to draw. So it's certainly not concerted. It's a multi-step mechanism. Okay? Definitely be comfortable with knowing how to draw that, because questions I've seen before, like you'll get 4 types of like reactions. They'll be like, one will be an SN2, one will be an E2, one will be a, you know, every one of each. And then usually there's a couple different energy diagrams, and you need to kind of do like a matching thing. Like this energy diagram matches an SN2 reaction or something like that. Cool. So there are some like, you know, quirks with SN1. So let's get familiar with them. And the best part is E1 is not really much like radically different than like doing the groundwork for SN1 will make E1 a breeze. So then we're almost done. Do some problems, we'll call it a day, and we'll have a good Sunday. But for SN1, what we need to worry about is, so let's do an example, something like this. We'll throw it back to, throw a tosylate on here. Good leaving group. So let's just say it's something like this. Okay, so secondary substrate, that's good enough for carbocation formation, right? Because that's something we need to, that's what we need to worry about. Then we have a polar protic solvent, right? This acetic acid right here. So I hope you're seeing this right here. That is what makes our solvent kind of like our nucleophile that's going to also double as the solvent. That's what we're going with here. We have protic character, so polar protic, and have a good leaving group in the tosylate, and obviously this is not a good nucleophile, so we're a check across the board. So the very first thing that's going to happen is that solvolysis will occur, and we have this. So every time you form a carbocation, from now and forever, freeze and think to yourself, can I improve this carbocation? Is there anything I can shift, whether it be a methyl shift or a hydride shift, to make this thing more stable? And so you have to look around and just say, okay, if I went from secondary to secondary, that wouldn't really help me out at all. So not really concerned with that. However, there's secondary, and then there's a tertiary situation over here. There's an H right here. So we can do a hydride shift here and improve the stability of this carbocation. So you have to do that. So you can do this. You actually start your arrow at the bond with the electrons and just say, I'm literally going to pick up this H with 2 electrons, and I'm moving it next door. This. So at that point, we have this now, because this hydrogen that I'll draw an asterisk on is right here. So it physically moved. Okay, so now we've improved the carbocation the best we can, so we can move forward with the SN1 attack. So I'm going to go ahead and draw my acetic acid. Make sure to attack with the right oxygen. It's the one with the alcohol character part. It's going to be a little crowded, but... Okay, so I got this right here. And I'm actually going to stop for a second, because the one thing you do, so you have to worry about shifts, but with SN1, right, at this point in time, we've made a carbocation. That carbocation is it's sp2 hybridized. It's flat, it's planar, it has trigonoplanar geometry. So whenever this attack happens here, whatever nucleophile you're working with, there's no preference for this nucleophile to come from here or here, above or below. So in a 50-50 split, equal amounts, that's the nucleophile will do this 50% of the time and this 50% of the time. So you have to be careful, because if when you add the nucleophile, if it produces a stereocenter, you need to show that. So if we look at this right here, we think to ourselves, okay, there's this isopropyl group, there's this propyl group, and there's this methyl group, and then this. Yeah, I just made a stereocenter. So what you can do is you just have to pick one. I'm just going to say, let's make this a wedge. which means something has to be a dash. So that is kind of like what we made. So to finish this reaction off, I just have to deprotonate this guy. I'm just going to use the tosylate from the beginning. Sorry, I'm a little all over the place. Okay, this is our final product, and because we produced the enantiomer in an equal amount, what I think is the best thing to do is on a test just write plus enantiomer, or actually draw the whole structure, right? Which would look like this. This would be a wedge. This would be a dash. So just it's important to know that when you do SN2 and you produce a stereocenter, because the attack can happen equal amounts from above and below, you produce you have a pair of enantiomers, and because this is a 50-50 split, I hope you're sitting at your computer saying out loud that this is a racemic mixture. So that's very, very important to just know that it's a racemic mixture, and that I feel like another good true and false question is when some people ask, like, an SN1 reaction occurs and it was observed that the plane of polarized light is not like because if you're chiral, you can bend the plane of polarized light. You exhibit optical activity. Sorry, I'm just tripping over my words. But when you have a racemic mixture, right, this thing, if it wants to bend light one way, its enantiomer bends light equally and opposite, right? So they just cancel each other out. Cool. So we'll do this one more time. We'll draw an energy diagram because this is a bit of a doozy. It's kind of like the true test if you are an energy diagram pro. So what I would say is let's go through this, and we have the solvolysis step right here. So I went from here to higher in energy, right? Because we got more unstable. Then an attack happened, so we went way down lower. We had solvolysis happen right here, and then we actually had the hydride shift. So we're still unstable. We got slightly more stable, so we're like down here. Then the attack happened, and then the cleanup. So it's like here was solvolysis. Then we had the hydride shift, we got a little bit more stable, still very unstable. Then the attack happened, and then acid base. So it's all about just stepping through the mechanism, identifying how many steps you've had, whether you get more or less stable from one to the next. Cool. All right, we'll do one more, actually, you know what, we'll save that for the end. We'll charge through an E1, and then we will just do some problems, and then call it a day. Hope everyone's having a lovely, lovely Sunday today. Okay, so E1. Luckily with E1, so E1 is always referred to, and like it's actually said this way in like textbooks, it's called a minor product. The thing is, anytime you do SN1, you're always gonna have an E1 minor product, always. And it's really difficult, nearly impossible, like is impossible to just like have like an E1 as your major product. You can only just do things to get more E1 product, but you're always gonna predominantly have SN1 as your product whenever you have like the reaction conditions for it. So we still want to be highly substituted. The only thing that really kind of changes here is we want a weak nucleophile, but we want it to act, it's like we want it to act as a base. It's not this. Good leaving group, polar protic. So if we took this reaction that we did for SN1, this is what we're gonna get. I'm gonna switch my black marker's kind of fading on me a little bit. Cool. Okay, so for this to happen, the same exact steps are going to have to occur. We have solvolysis occur, we have our leaving group leave. Then we have our, instead of an SN, a substitution attack, we just do an elimination step. We look to our neighbor, grab the hydrogen, electron swing down. Leaving group doesn't have to leave because it already left. So that's all we have to do. Quick and easy and dirty. So what's really tough, right, is maybe you're just thinking to yourself, but why can't we just use a stronger base? Then we'll definitely get more E1 product. However, the reason why E1 is kind of in this weird place is because if that was what we were going to do, let's say we were just going to swap water out for hydroxide, well, what's going to happen then is this is it's more reactive to the point where it's not going to wait for solvolysis to happen. It would just do E2. It would just react, you know what I mean? That's why E1's in this weird place. Because if you grab the base that you want to do more elimination, it's not going to wait for the solvolysis part to happen. It's just going to go ahead and do an E2 elimination. So the thing is with E2, or E1 rather, we need to look out for shifts. Shifts are in play. And let's do an example, and then I'll explain what you can do to kind of get a little bit more E1 product when you want some E1 product. So let's do this. I'm going to drop a little bit more to the left, give myself some room. Okay, I'm going to explain why the heat for the triangle for heat is there, the delta. Okay, so this is our problem. And I'm just going to say, like, let's just draw the E1 product. Make it very, very blatantly obvious. So solvolysis happens. Carbocation right here. Right, remember we have to freeze and think to ourselves, can we make this better? Well, in fact, we just look straight down right here, and we can do a hydride shift. So I'm going to yeet this hydrogen right up there. That H is up now here. Asterisking it just for clarity. And now we just do our elimination. So when you do E1, you always just want to make the most substituted bond. That is what you're going for. Oh, and I'm realizing I kind of made this a weird example, so I'm gonna just erase this just so, yeah, no confusion. Okay, cool. So yeah, we have to make the most substituted double bond that we can. So right here, it's going to be this tertiary bond. So really the shift didn't do anything, but that was what we had to do. So ethanol will be our base. We're going to actually grab the hydrogen we just moved. Big double bond right there. So our product is that, oh, not that, this right here. Okay, cool. All right, so why I included this, the delta, the one thing you can do I'll keep this up. The one thing we can do to increase our E1 product is to add some heat. So if we looked at this like from a reactant and product perspective, we had two reactants, that being our substrate plus ethanol, and we made we have ethanol at the end, ETOH2 plus, like that right there, and we have also this I minus. So again, maybe one thing is maybe it's, you could represent this with just ethanol and this being like HI or whatever. We went from two things to three things. Okay, so if we're going to bring back a good friend of ours, if we bring back the Gibbs free energy equation, so in this reaction, we know that delta H is going to be negative, right? Because it's exothermic, it's going to give off some heat. We know that's always a given. So if we need to really drill into this, like if we want this reaction to be better, we want the delta G to be more negative, right? We want it to be more negative because that means it's more spontaneous. Can't do anything about delta H. The bonds we break and form those are kind of set for us. However, So if we drill into the entropy of this reaction, right, going from 2 to 3 things from a disorder perspective is very good. That means like the delta S for E1 reactions is very good, and in entropy land, that means your delta S is positive. That's a good thing. Different convention than the delta H. So the way we can make delta G more negative is because the entropy is positive, right? This is a plus sign, and we want delta G to get more negative. So if we can make this value bigger, right? We'll be subtracting a bigger negative number. Delta G gets more negative. So if we crank the heat up with this temperature, if we run this at higher T, the delta G of our E1 product or our E1 reaction gets better. So a really popular kind of question is like, how do you get more E1 product? Well, you run it at high temperature. Or maybe how do you make sure you get less E1 product and more SN1? You'd run it at low temperature because that means the delta G would get worse for E1. Okay? Whew. All right, gang. We have done a lot of things today. So let's do some examples and then we will wrap it up. But I hope at this point in the program, you're thinking to yourself, wow, I definitely feel more comfortable, understanding the inner workings of, SN2, E2, SN1, E1, and I hope these examples, you're able to tell what they are before I even tell them what they are. So let's do something like this. Okay, so easiest thing is to look at your solvent, right? Because if it's polar aprotic, we're going to work with SN2 and E2, and if it's polar protic, we're going to work with SN1, E1. So DMF, we know that's polar aprotic, so we're going to forget about SN1 and E1. We're only going to focus on SN2 and E2 because we have polar aprotic solvent right here. And then I hope that you're seeing, okay, my substrate right here is primary. That is really, and we have a good nucleophile in CN minus, right? So those are two things that scream, we're not using a base to make a double bond, we're definitely doing substitution. This is an SN2 problem. So at this point, then think to yourself, do I have to worry about stereochemistry and inverting it in my product? Luckily, we don't. So all you need to do here is actually perform the substitution. And there you go. That would be the answer. Okay? Let's do another. Okay. What we got here is, so we have like a multi-step problem here. So I hope the first thing that jumps out to you is you're thinking to yourself, we don't even have a good leaving group in this problem, right? Like OH, hydroxide, terrible leaving group. Well, the first step in this problem is meant as a protonation step. So the very first thing would be, I'm trying to draw abbreviated SO3H, there we go. Sulfuric acid, drawing it in an easy way. So the very first thing is that this OH is going to get protonated, and just for space, I'll just do this. It's going to get protonated, and then at this point, right, now we can kind of evaluate what situation we have. I hope you're thinking to yourself, okay, secondary carbon, now we have a good leaving group, polar protic environment, so polar protic, so we're definitely working with SN1, E1, and I hope you think to yourself, I don't see heat anywhere, so I'm just going to worry about forming the major SN1 product. So, but remember, since we're in SN1 land, we should draw the carbocation that we form and see if we can shift it and make it better. So after the leaving group leaves, we have this situation. And I hope you freeze. and then think to yourself, okay, I'm not going to do a secondary move, and I don't see any hydrogens up north above. However, that's a quaternary carbon. We can do a methyl shift. And then whenever you shift and you like have wedges and dashes, just draw them as straight lines, because we would just be guessing if we knew what they were. You know what I mean? So at this point, I know I have my plus charge here. Cool. All right. So then now we can have the ethanol come in and attack. And remember, we just produced the stereo center, so I'm just going to go ahead and pick like a wedge for my ethanol. That flat methyl group flips down to be a dash. I need a cleanup step. I'm just gonna skip the cleanup step for space. So our final product looks like this, and I hope you are at your computer screaming, Joe, don't forget to write plus an antimer, because you need it. Okay? So, to kind of pick that apart again, remember, we started out with this bad leaving group. We had a first step to protonate our leaving group to make it a good leaving group. Then we saw we were in a polar protic environment, so it was SN1 or E1. We didn't see heat, so we knew, it has to be SN1. Leaving group left, we had to stop, we had to shift, to do a methyl shift to improve our carbocation. Then we attacked and did the rest, and we knew we produced a stereo center because in SN1, we're attacking an sp2 carbon, which means we don't have any problem attacking from this angle or this angle. And then, so we just knew we had to pick one enantiomer to show, but then write plus an enantiomer to make sure we got all of our points. Okay? Okay, so at this point, I'm going to do some of Arena's problems, and then we're going to call it a day. Okay. Okay. Let me get some of these problems up. 1 second. And I'm going to move my computer over here. Okay. So for example, there's a section that says try and draw some of the following. And for the first one, it just says a poor electrophile for SN2, right? So a poor electrophile would be something not negative, like water. Boom. Poor leaving group that can be made into a good leaving group through protonation. Well, we just saw an example of that, right? So like, let's just say, for example, I just redrew that, just any alcohol, right? With something like H2SO4, or you could just use like H3O+. We can protonate OH to OH2+, which is just water, right? So that's a good leaving group we can protonate to make better. A polar protic solvent. Well, we could just use water, but I use something like ethanol. A charged molecule that can be a good nucleophile. Oh, okay. So something like Cn-. That's a great nucleophile, or like I-. A strong base for an E2 reaction. So I'll give you two. NH2- for a small base, and something like LDA or potassium terbutoxide for our big bulky bases. Okay, so then let's look at some of these other ones. I liked this one problem down here, which had this reaction listed right here. H there. It's an SN2 reaction. And the problem says that, someone completed this reaction, and it said like a student made a remark about the problem by saying that there's an issue with this, that there was no stereochemical inversion done when the person completed this problem. However, we don't need to show any stereochemical conversion in this SN2 reaction because this is not a stereocenter, right? Because we're not attached to 4 different things. Okay? So that was like the whole problem right there. Okay. Another one that's on that another problem from Marina was this thing right here. Let me draw this reaction for you guys. Erase this too. NaO. H. Okay, so basically this problem, it's written like this. Oh, it has the product also, but it's like a theory problem. This is the problem, and it says, like, I guess the aim of the problem was to do SN2, but the problem also states that SN1 can be done with this this reaction as well. Why is that the case? So if you're thinking to yourself, okay, well that's weird because this is a primary spot, right? So the formation of a primary carbocation is not good. So why would SN1 happen here, right? We would make this carbocation. The reason is because this is resonance stabilized. So even though it's deceiving, it's SN1 normally would not happen, but the fact that this carbocation is stabilized by a whole heckin' lot of resonance, not only can this structure, support SN2, but it can also do SN1. Alright, cool. That's really the whole problem. Just basically saying, yeah, this can happen. I know, like, it looks like a primary carbocation. However, it's allylic, so there's a lot of resonance. It's resonance stabilized. SN1 can happen. Okay, I think we got 2 more. Next one gives you this type of structure, which looks weird, but it's not scary, I promise. Okay, so you might be thinking, like, what the hell is this? All this is a different way of drawing a cyclohexane ring, because 1, 2, 3, 4, 5, and 6. It's a very convenient way to draw stuff. I know saying the word convenient might sound silly looking at this because you're like, what is this? If I just draw a ring and I just realize that I have on carbon 3 right here, I have a bromine going down, and then I have 2 carbons above the ring connected between 3 and 6, right? So that's this carbon and this carbon. It's weird because it's like there's a wedge carbon right here, there's a wedge here, and those 2 carbons are connected. So that's weird to draw in a flat way, right? So that's why like this 3D method is kind of preferred. So this problem says that when this structure undergoes SN1, no racemic mixture is observed, and actually the resulting product bends the plane of polarized light, which is weird, right? Because we know in SN1 we attack a carbocation from above and below and make a racemic mixture. It shouldn't have any optical activity, the product mixture. The reason why this doesn't display that is because the moment this bromine leaves, the bridge, it's the bridge up top, right? Once this leaving group is gone, this bridge stays there. So when this occurs, here I'll show it on this. When this leaves right here, this bridge isn't going anywhere because it's attached to this carbon and this carbon. So things are always going to attack from the other side like that, and you're never going to get, you'll never produce a racemic mixture since the having no preference thing doesn't apply here. Does that make sense? Just ask the camera. It makes sense. Cool. And last but not least, oh, this is unfortunate. The problem is just like a big biological structure. I'll just draw the parts that matter. One sec. Think about the best way to do this. One second, guys. Thanks for being patient. Basically, I'm drawing just like a snippet of the problem because it's a lot. But basically, it gives you two reaction arrows like this. And it's saying what is the best, like reaction A or reaction B. What situation actually supports a successful E2 reaction? So what I hope you guys are thinking, so it's not even asking you to do anything. It's just saying like, just pick which one is the better E2 reaction. I hope you're looking at this and thinking to yourself, well, this is weird, but down below in B, I want to eliminate this chlorine, that's a dash. And because I want the double bond here, right, I have to work with this hydrogen right here. Damn, I can't do that in B because we don't have the anti-peri planar setup. We have a cis-peri planar setup. So B, that's a no-go as far as that E2 reaction happening. Up here, these two H's will definitely support this elimination reaction to happen. And that does it, gang. So thank you for tuning in. There will definitely be a third exam, like live review, and one for the final. So in the meantime, if you have a test this week, good luck. If you're listening, thanks for popping by. For the next time, make sure to tell your friends about the site. Make sure to follow me on Instagram, YouTube, like me on Facebook. Subscribe on YouTube. Send me problems. Arena, thank you for doing that. I hope this was helpful and I did some of the ones that you maybe had some issues with or were curious about. But thanks again for tuning in. You guys are organic warriors, and I will see you in the next review.